Hello, everyone. Good afternoon. Can you hear me? Great. Hope you all had a good weekend and got a chance to enjoy the great weather we had. Okay, so today I plan to go over exam 1 and then talk about lab 2, which we're assigning today. You should have got an email from Charles about that a few minutes ago. And then we will continue talking about real-time systems. So I'm going to go ahead and share this, and hopefully the slide doesn't get, well, actually, I could probably just present it from here. Okay, so exam 1, as you remember, we had last week on Wednesday. There were 15 questions. If you look at the grade distribution, it's pretty much a perfect looking Gaussian distribution with a mean of 64.3%, which is obviously lower than I expected it to be based on the grades on quizzes 1 through 3. So obviously we're probably going to have a curve at the end of the semester. So don't panic about this if you didn't do very well on here. I also broke down the percentages on each of the individual questions. It looks like there was 3 of them in particular that averaged under 50%. That would be question 3, 6, and 13. And we'll go over those as well as all the other questions as well. So you guys will be ready for the this material when we have it on the final exam, because the final exam is comprehensive. And of course, this we'll have this lecture up too. So when you're studying for your final, you might need to refer back to this to refresh your memory on this stuff. Okay, so question 1 says that a peripheral spans I/O addresses 100,100 in hex to 10EFFF. What is the size of its address space? So this one, let's see, well, this one was 57%. So this question actually was kind of low, maybe because I didn't I didn't cover it very long. So how do you do this? Well, you subtract and add 1. You subtract the upper range from the lower range, and you add 1. You add 1 because the addresses are inclusive. So 10EFFF minus 100100. You just do this in do hexadecimal subtraction, and that gives you, if I did this right, EEFF. So the F minus 0 is F minus 0 is F minus 1 is E minus 0 is E, right? And then 1 minus 0 is 0, 1 minus 1 is 0. Okay, so EEFF, hopefully I did that right. And then you need to add 1 to that because we're including the first and the last address in the address space. So EEFF in base 16 plus 1 is EF00. Now the problem is that you have to then convert this from base 16 to base 10 because all of the answers were in base 10. And so I usually just use like Windows or the calculator app in Windows, or I think Linux has the same thing, or at least in Ubuntu. Or there's converters online, or if you want to do it by hand, the idea is that each of these digits has a significance of a power of 16. So starting from the leftmost digit, this E is basically 14, and that would be multiplied against 16 to the 3rd power, because the 4th digit to the right would have a significance of 16 to the 3rd power. So that would be 14 times 16 to the 3rd power plus, and then the F is 15. So that'd be 15 times 16 to the 2nd power because it's in digit position 2. Remember, when you look at these digit positions, it's from the right to the left, starts at 0. And so that gives you 61,184 bytes is the answer there. Okay, question 2, which line of code will set bit 3 in variable val to 0? Let's see, question 2 is 87%. Looks like this one was pretty easy. So this was val, you take val and then you take 1, shift it 3 bits to the left, and then do the complement of that, which will give you a temporary value that's all 1s except for a 0 in the bit position 3. And then you AND that with val. It's like a bit mask, and then you use the ampersand equals as you assign the result of that back to val. So that was, I think, pretty much read out of the slides. Okay, question 3, which line of code will insert the value 7? Now this one, I think question 3 was the lowest. Yeah. Well, question 3 and question 13 were both only 35% of you got those 2 questions right. This one was not exactly from the slide. Wasn't taken directly from the slides. This one was a little bit of a variation. So the idea is that we have the value of 7. The value 7 requires at least 3 bits because 7 is 111. And we want to insert it into variable val, and we want to put it into a bit field spanning bit positions 9 down to 7. This question, by the way, I went back and forth with Charles about how exactly to word this one, because my original wording, Charles said was no good. I rewrote it. I don't know if this was confusing or, but we want to take the value of 7 and we want to put it into a bit field that spans 9 down to 7. Bits 9 down to 7. Now, bits 9 down to 7 is 3 bits. Now, you could ask, well, wait a second. What if the value 7 is already in that bit field, or what if there's another value in there, something besides 0? Well, if you look at the answers, the only one that makes any sense is to take the value of 7 and shift it 7 bits to the left, and then OR it or merge it into val, using the bar equals. So I tried to show that here graphically. So if val was originally, okay, so I'm showing bits 9 down to 0 here. Val might be more than 9 bits, but I just showed the least significant 9 bit, or actually least significant 10 bits here, 9 down to 0. And then we take this temporary value and we shift it 7. So we take 7, which would have been 111 in the least significant 3 bits. And if you shift that 7 bits to the left, then that result will be basically maneuvering the value of 7 into bits 9 down to 7 in the temporary value. And then you have to do a bitwise OR to merge it or to kind of insert it into those same bit positions in val. So we just do a bitwise OR. Now, if there was already data in those bits, then if there was already, yeah, that's a good note from Charles, and maybe that was the confusion. This is not a general case solution. See, this worked out. I guess one reason this worked out because it made it simple, gave a simple answer, is because 111 are all 1 bits. Yeah, that was on. Yeah, Charles said I assumed it was on purpose. Yeah, so that was the. I guess maybe that might have been the confusing part here. This is a kind of a specialized case because it's 111. If there was a 0 in there, then I would have had to 0 out those bits 9 down to 7 in val before I did this. So there would have been an extra step. But because it was 111, I guaranteed that regardless of what was in there before, I'll end up with 111 in those bit positions afterwards. So that's the idea. Like I said, I showed, I talked about how to do multi-bit extraction, where we basically took a bit field and shifted it to the right or bit masked it out. In this case, it basically is just kind of doing the opposite, which is just setting bits into a value. So that was the idea there. I understand this one was kind of tricky because, like I said, it didn't come straight out of the examples I showed, and it's not a general case general case solution, as Charles mentioned. Okay, question 4: a 5-volt PWM signal has an apparent an apparent analog voltage of 3.75 volts. What is its duty cycle? See, this was question. Oh yeah, this was. I guess this was the easiest one of all. 95% of you got this one right, and this was just 3.75 divided by 5 is 75%. Question 5: assume a CPU has an interrupt handler that requires 20 milliseconds to execute, and that the interrupt controller is rising edge triggered with no acknowledge. Which one of the following describes the minimum interrupt frequency that would cause the CPU to skip servicing one or more interrupt events? Well, this one gives you some information that's not really relevant. The fact that it's rising edge triggered isn't relevant here at all. It doesn't really matter if it's rising edge triggered. If it's, if you can issue 50 interrupts per second, regardless of its, if it's rising edge triggered or not, regardless of how you actually tell the CPU that interrupt is occurring, if you issue more than 50 interrupts per second, then the CPU is going to miss interrupts because it's going to take longer to process the interrupt than the timing between interrupts. So that was basically 1 divided by 20, which is, did I write that right? 20 millisecond. Yeah, 1 divided by 0.02, 50 interrupts per second. So that was question 5. That was 74. That was pretty easy, it looks like. Question 6. A device connected to a UART channel with odd parity receives value 74 in hex and parity bit 1. I think this one was one of the tougher ones. Yeah, question 6 was 47%. So this one, the idea is that if you look at 74 in hex and convert it to binary, it's 0, 1, 1, 1 is the 7, and the 4 is 0, 1, 0, 0. That has 4 1-bits set. If the parity bit is set to 1, then you would have 5 total 1-bits, and so that would be consistent with odd parity. So that would mean there's probably no transmission error. Although, as Charles pointed out last time, you could have, for example, 2-bit flips and parity wouldn't catch it. But when I say probably, it's much more likely, well, it's generally the case, it'd be more likely that there'd be no error than 2-bit errors. So I said the answer is there's probably no bit error, just because the number of 1-bits is odd. Okay, question 7. What can you infer from the SPI transaction shown below? So this is kind of an open-ended question, obviously, but if you have to look at you have to kind of evaluate each of the options to figure out which one makes sense. If you look at this, though, even without looking at the options, you should notice that we have some traffic on MISO, which means that we've got data coming from the slave back to the master, which means it's probably a read. I say it's a transaction, and there's obviously 16 bits here, 16 clock cycles. So I call it a transaction. There are 2 exchanges. It's probably a read or write. I can see in the second exchange there's some activity on MISO. There's some when I say activity, I mean transitions, rising, falling edges. So that probably means that it's a read based on the fact that we've got data coming back to the master. So we got data going out the master, and then we got data coming back to the master. The data going out only happens in the first half of the transaction, the first exchange. The data coming back only happens in the second half. So that's probably a read transaction. And then you can tell a few other things. If you look at the clock before the transaction begins, it's 1. That probably means CPOL is 1. And you can see that the first time that the data changes is also the first time the clock changes. So the clock and the data change at the same time. That probably means that CFA is 1. And so, oh, I guess I didn't put the actual answer there. But I think basically it was read transaction, and I think one of these 2 was part of the correct answer. Question 8. What byte value is sent to the master in the first exchange? Okay, so this one was meant to actually kind of be a trick question a little bit. In fact, it's funny because when I wrote this question, and then when I went back and I did these slides to come up with the answers, I actually got it wrong, because I actually used the value going to the master in the second exchange, but it turns out that, and so that's literally how I did it. I said, well, the answer must be 10110000, which is B0. That was how I thought. That's what I initially thought, but then I was like, well, wait a second. It says the first exchange, which means that I was actually asking about the first byte transaction, which is this one, is all zeros. So yeah, I actually, like I said, that was a little tricky, because you might have gotten tricked into looking at the data being sent to the master in the second exchange as opposed to the first exchange. Obviously, the data, if this is a transaction, then the master would have ignored, zeros go back to the master, but those are, essentially don't cares. But the answer here is zeros. That was question 8. How do we do on question 8? Question 8 was 75. Okay, yeah, apparently I was, most of you by far were not fooled like I was on that one. Although I don't know if B0 might not have been an option. I don't remember. Okay, assume an SPI channel has CFA 0 and CPOL 0. What happens first during an exchange? So this one also was also a little open-ended. You had to look at the options here. The answer was the MOSI transitions to its first value. So the idea is that, the idea here is that MOSI and MISO change before the clock when CFA is 0. So that was the kind of the point of this one, is to understand what the CFA, what the implications of CFA are. So sorry, I'm just curious how everyone did on that one. 57, that was kind of a tough one. Question 9. Okay. Question 10, assume two devices are connected to the same wire using an open drain interface. One device attempts to set the wire's value to logic 1 and the other to logic 0. What is the resulting value? It would be logic 0 because the wire's natural state is logic 1, and so if anyone pulls it to logic 0, then it goes to logic 0. If one device is attempting to set the wire's value to logic 1, it means the device isn't doing anything. It's not actively engaging the wire at all. So that's why the answer here is logic 0. So, okay, sorry, I want to go back. Just curious. Question 10, 83. Yeah, you guys were fine with that. Okay, question 11. Consider the I squared C transaction. What portion of the transaction was not acknowledged? Okay, this one is kind of a pain, because you got to figure out, you have to divide this into bit slots, and then you have to divide it into the two parts, which is kind of the address and the data part. So that's kind of obnoxious, but luckily with I squared C, it's a little easier. It's easier than SPI, at least in my opinion, to figure out where the bit slots are, because you're just looking to where the clock is high. So to signify that, I just drew a line through, each time the clock was high, and then I just numbered them. And so the acknowledgement bits would be bit 9 and bit 18. And then the acknowledge is 0 means acknowledge. So that's another part of this is a little tricky, because the acknowledgement is active low. So 0 means, and obviously the reason for that is, as I mentioned, that if nobody is listening and no one's responding at all, then your acknowledge bit would be a 1. So this is meant to, the fact that acknowledge is active low is meant to catch cases where nobody's answering the phone on the other side, basically. So yeah, acknowledge is active low, bit 9, bit 18. Bit 9 is the acknowledge after the address bit, the address phase, address part after the address is sent. And then bit 18 is the acknowledge after the data part, and you can see that SDA bit is high in that case. So that's actually considered a NAC, or a not acknowledge. So the answer here is the NAC happens after the data phase. Read-write bit. Yeah, there's still a read-write bit, but we don't care about that in this question. The read-write bit would be bit. Wait a minute. Did I leave that out? I didn't leave that out, did I? Where does the read-write bit? Read-write bit is there's a 7-bit address, and yes, yeah. That's a good point. Yeah. Wait, did I say it was 8 bits? I might have said that. Yeah. So okay. So let me clarify this. So Phil raised an issue with this question when we were when I had them review the exam. He pointed out that I squared C has different variants with different address sizes. So now I mentioned in class that we're only looking at the 8-bit version of I squared C. So that's why I think I clarified that. I don't remember if I clarified it in this question, but what I meant by that was the whole address phase was 8 bits. So you have an 8-bit address phase and an 8-bit data phase, and in the address phase would include the read-write bit and any other flag bits that you would have in there. Although I squared C, I think they tend to have the bits locked down. But anyway, that's what I meant was 8 bits in total for the address phase. So the address phase was fine, but the data phase was apparently something happened. Now I don't know if this was a read or write. I guess it was it doesn't matter, because either the master, if it was a write, the master would have been sending the data. If it was a read, the slave would have been sending a data. But either way, whoever received the data or whoever was supposed to receive the data would have issued a knack. So that's the part that would not have been acknowledged. So that's the idea there. Yeah. So another I squared C channel question 12. Which side of an I squared C channel has control of SDA during the time in which the STL signal is high for the 17th time during a transaction? Okay, yeah, this is a little bit tricky. So this is the 17th bit slot. So obviously this would be in the data portion of the transaction. But 17, so I mentioned that the 18th time would have been the acknowledgement. So the 17th time would have been this guy, would have been basically the last bit of the data portion that comes before the acknowledge. So who's sending data, basically, is what the question is asking. Well, it depends if it's a read or a write. So if it's a read, cycles 1 to 8 would be the master sending the address and the read-write flag. Cycle 9 would be the slave acknowledging, and cycles 10 through 17, which, yeah, if you look at this chart, it's a little easier to see. Cycles 10 through 17 would be the slave driving the data, the SDA, and then the master would acknowledge in cycle 18. Whereas if it's a write, cycle 1 to 8 would still be the master sending the address. Cycle 9 would still be the slave with the acknowledge. But the difference is that the data portion would be controlled by the master, and then the acknowledgement of the data would be the slave. The only thing we care about, though, obviously, is cycle 17. So basically, the answer is if it's a read, it's the slave. If it's the master, sorry, if it's a read, it's the slave is in control, and if it's a write, it's the master is in control. So that's the 17th, basically 17th clock cycle. So that was a little, yeah. I think that you had to. I think it's in that case you almost have to write it out, kind of like I did here, to figure out what's going on. Okay, question. What was question 12? I'm just curious what the score on that one was. 78. Yeah. Oh, yeah. So that one was good. Everyone, that was a high scoring question. Okay, question 13. This was the other one that was the lowest score. Which of the following is the transfer function of an LTI derivative of f of t with respect to t equals the second derivative of g of t with respect to t. That is, formatting is wrong. I just noticed that. There we go. Obviously, the formatting, this is not the same formatting that was in the question because it's just all text. But anyway, so where g is the output. So this is, if you're doing a transfer function, you have to know what's the output and the input. So this one, you have to do the Laplace transform. And I think what some of you might have forgotten here, and because I forgot it when I was writing up the answers here, tripped myself up again with this one, is you have to multiply. So for the first derivative, f of t, when you convert that to f of s for the Laplace domain, you have to multiply that by s. So you end up with an s on the left-hand side. And then the second derivative is multiplying g of s by s squared on the right-hand side. So then you f of s over g of s is s squared over s, or just s. But because this form of the transfer function would be f is the output, right? If you want g to be the output and f to be the input, you have to take the reciprocal of both sides of the equation. So the answer is 1 over s. So you have to calculate g of s over f of s. So yeah, initially I forgot about that s on the left-hand side when I was working this out, when I was reworking it out, when I was doing the slides. I think that might have been the confusion, or you might have been tripped up by the form of the transfer function where, you know, the output has to be in the numerator on the left-hand side of the equation and the input is in the denominator. So that was a simple one, but it was easy to, it's easy to get confused there. Question 14, what is the Tustin transform of transfer function s over s squared with t equals 1? So this one you just have to substitute in 2 times z minus 1 divided by t times z plus 1 for s. And now this one, if you work it out the way I did here on this third bullet down, you can actually reduce it down to 2 times z plus 1 over 4 times z minus 1. You know, using these steps that I have on the third bullet down. Unfortunately, that was not one of the. That's a correct answer, but that wasn't one of the responses. That wasn't one of the options. And the reason is because instead of working it out like this, I actually multiplied out the numerator and the denominator here, and basically expanded them to a order 3 polynomial, and that's also a correct answer. It's just not minimized. It's not reduced. So these two answers are equivalent to one another. It's just that the one on the top here is the kind of the factored out form of the one on the bottom. So this was a little tricky because you had to realize that you had to, you know, sort of get it into an order 3, you know, a ratio of 2 order 3 polynomials, which is not the sort of the simplest form. So this is just, you know, essentially just doing the polynomial multiplications. But I think this one actually, yeah, I mean, you guys did really well on question 14. So that apparently didn't mess a lot of you up. Okay, question 15 is, what is a z domain transfer function of f of t equals g of t plus 2g of t minus 1 plus f of t minus 1? This one is basically doing a z transform. The z transform is not quite as straightforward as the s transform is, as the Laplace transform. So for this, but I mean, it's not too bad. And actually, this is actually, there's a typo here. Sorry, this should be of f of z. Sorry about that. Yeah, these should all be z's instead of s's. Sorry. Let's force a habit putting s in there. But basically, the idea with this is you convert the f of t's and the g of t's to capital F of z and capital G of z. And then you multiply those by z to the negative first power whenever you are referencing a sample from one sample in the past, which would be t minus 1. Sorry, let me fix these other two. Sorry for the typo there. I just too used to putting that's in there. Okay, so for example, so f of t is f of z, g of t is g of z, and we have a coefficient of 2 that stays in, and then g of t minus 1 is converted to g of z multiplied by z minus 1, and likewise f of t minus 1 is converted to f of z multiplied by z minus 1. Now the tricky part is now you have to get all of the f terms on one side and g terms on the other, and so you can just you can subtract the z to the minus 1 times f of z on both sides, and so you end up with this, which has f's on the left, g's on the right, and then you can factor out the f of z and the g of z on the left and right, and then you can build your transfer function, which, let's see, the output you can tell from the time the time domain is, the f of t is the output, g of t is the input based on that form. So we want f of z divided by g of z, and then you would end up with a ratio of 1 plus 2 of z times negative 1 and 1 minus z to the negative first power. And the problem is you can't leave it in that form because you end up with a you want to have well, actually you could leave it in that form. I'm sorry. There's no, if you're doing a transfer function, you can leave it in that form, but that wasn't one of the options. You want to multiply this guy by z over z so you can get it into a form where you have a proper polynomial in the numerator and denominator. Sorry, I was thinking that when you go the opposite way and you go to the time domain, you have to make sure that all of the powers of z are negative or 0 or negative. But in this case, it doesn't matter. You're coming up with the transfer function, so you can leave it in the form, you want to have it in a ratio of 2 polynomials. So that's it. Let's see, how do we do on question 15? Question 15 was 60%, so y'all did well on that one. How accurate is our grade average on Dropbox without the curve? That's a good question. I don't think it's accurate because unless Charles or Philip, unless Charles or Philip set up Moodle with the weights. Okay, so Charles's message indicates that he did not set it up with the weights, and I didn't either. And even if we did, the problem is that you're only seeing it's not really accurate until the end. So yeah, you'd have to look at the quiz. You'd have to look at the grade weightings on the syllabus. We haven't the grade that you have on Moodle is not intended to be an indication of where you're standing. Unfortunately, I could set it up. I have set it up like that in the past, where I had grade groups and weights on Moodle, but so there's not a curve for the exam. We'll curve the final score at the end. We curve the final course grade. But I would be interested to know if any of you have any feedback on the exam. I'm kind of surprised because the quiz grades were really high. and the exam was, lower than I expected it. So I'm guessing maybe it was too long, for the 75 minutes. I have it budgeted here for 5 minutes per question. Obviously a question like, the ones we have to work out in algebra, like question 15 and 14, obviously take more than 5 minutes. But then there's other questions that are, should be pretty quick. So I was hoping that on average it would be 5 minutes, but I might have been being too ambitious there. Yeah, if any of you want to send me an email, let me know what you think. Give me some feedback on the exam. I'd be happy to know. I'd like to know. Any feedback would be helpful. Okay. Yeah. We spent. Yeah, maybe it was the topic, the control. The control theory we didn't spend as much time on, although the scores were pretty decent for those, except for that one, that question 13. Okay. Okay. Yeah. So I'll probably budget a little bit more. I think Moodle does keep track of that. Yeah, Moodle collects a lot of statistics. I'll have to check. We can go back and check to see how much time was spent on each question. That's a good point, Charles. But I might have to go. Maybe I'll go. Bump up the time per question, maybe to 7 minutes or something like that for the next one. It's hard to calibrate, when you're doing multiple choice, because when you do a regular exam, it's kind of you base it on how much the student would have to physically write down. But when you're doing multiple choice, it's harder to predict that. Okay, so I'm going to switch over now to lab 2. Okay, so we have our second lab. It's been assigned today. We're gonna give you. It'll be due on 16th, Charles. I think that's what we said.
No, it was 9th, Friday.
Yes, sorry. So basically, you'll have this week, next week, and the week after to get it done. So basically 3 weeks, not 3 full weeks, but you have 3 school weeks to finish this. So keep that in mind. Try not to wait to the last. Whoops, sorry, I don't want to maximize that because I'm afraid it'll screw up. Wait, hopefully you guys can see this. Can you guys see the slide? Hopefully you can see it. Charles, can you see the slide?
I can see it. Yeah, it does have that weird border thing, but since you have it not in full screen, it's okay.
Okay, I don't know why the sharing is okay. Anyway, okay, lab 2. So you've got 3 school weeks to do it. The objectives it's similar to the first lab in that you are asked to read a trace file. So the idea is that you have to imagine that you've collected some data using an instrument, a laboratory, like an oscilloscope, or actually a logic analyzer rather would be more likely, and you've saved, or you've simulated, or you've done a simulation, and you're reading that and you want to interpret the data in there. So you're basically decoding a trace file. Now, as Charles mentions, that the templates are pretty much the same as the last lab. So the last lab was designed to kind of get you used to the framework and the API that we've provided and the data files that we're giving you, these trace files. Now, if we were in the lab, we would be actually measuring this on an actual oscilloscope. But you have to just imagine that you've already kind of recorded this data into a trace file. As we mentioned in the last lab, the trace files are of a proprietary format that Charles invented. There are trace file formats that are standardized. I think the most well-known one is probably the value change dump, but that's a fairly complex format. So we've simplified it for you, so you can actually open the text file, and see. It's kind of like a table. It's tabular. So every line of the file represents the state of the signals being collected when any one signal changes. But you don't have to read that file directly. You can read it through our API. And so the goal of this lab is to decode Yes, oh, Charles mentions that there's a way to convert between BCD and the format we use. So the objective is to decode SPI transactions. And so we're going to start out in the first part of the lab, we're going to lock down the values of CPOL and CFA to 0 and 1. And we'll be doing a read and write transactions. Okay, so that's the first part.
Was it 0 and 1?
Is it 0? Did I get it wrong? It might be 0 and
Hang on, I'll double check it just to
oh,
be
sorry.
sure.
No, you're right. It's 0 and 0 actually. Sorry. Sorry. I think it's 0 and 0 actually. Yeah, Charles, if you could double check that, that'd be great. Yeah, I might have wrote that down wrong. The point is that in the first part, we're gonna lock down. We're gonna tell you CPOL and CFA, and then in the last part of the lab, the third part, you're gonna have to be able to decode transactions with arbitrary CPOL and CFA. So in the first part of the lab, CPOL and CFA are 0, 0. I was able to tell just by advancing one slide, and I can see that you can tell here that the MOSI changes before the clock in this waveform. So the CFA is 0. It also says that there too at the top. But anyway, so CPOL and CFA are 0, 0 for parts 1 and 2, and part 3 you have to be able to support other CPOL CFA settings. In the first part, you're going to be decoding the 2 exchange transactions, meaning that those are transactions that involve a single byte being read or written, and it requires 2 exchanges because the first exchange is the address and the second exchange is the data. The second part is where you'll be decoding streaming transactions that allow you to read or write multiple bytes within one transaction. And so that involves 3 or more exchanges. And then the third part, as I mentioned, you're going to be decoding either to exchange or streaming with arbitrary CPOL or CFA. Yes, that's a great question. So, and I'll get to that about our CPOL and CFA given for each test. They are, and I'll show you how to get those values. Okay, so let's take a look here at a transaction, an SPI transaction. Okay, so I mentioned CPOL and CFA are 0. I can easily verify that by looking at what the clock is before the transaction. It's 0, so CPOL is 0. That's the clock polarity, and I can verify that CFA is 0 by checking when the MOSI and MESO have their first transition relative to the clock, and since they get a head start on the clock by a half a clock cycle, then CFA is 0. That's again the clock phase. Okay, so in order to see what the data is being sent and what data is being sent, we need to basically we're looking at, in this case, the data is going to be sampled on the rising edge of the clock. And so I've drawn dotted lines here, a half a clock cycle before and after the rising edge of the clock. And another way to think of this is, you start whenever the MOSI and MESO start to change, and you give it one cycle to hold that bit, and then of course the rising edge of the clock should be right in the middle of that. Okay, so I've marked this up to show the data being sent on MOSI and MESO, and you can see that there should be 16 bit times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, you can see 16 bits. And we've got MOSI active in the first 8 bits and MESO active in the second 8 bits. That means it's a read operation. And so I mentioned in the lecture that when you're doing transactions over SPI, it's the way that you interpret the data in the first exchange is kind of arbitrary. It's just up to the vendor, whoever you're talking to, basically. So Charles has come up with these the bit pattern, what the bits mean in the first exchange. And so address bits 7 down to 2, the most significant 6 bits, 7 down to 2 is the address. So there's a 6-bit address. And then bit 1 is a bit that designates whether the master intends to read or write. And read is marked as, it would be specified as a 0 in this bit position, and write would be specified as a 1 in that bit position. Okay, and yeah, as Charles mentions that we made up this protocol, but it's actually based on the protocol that was used by the accelerometer that we used in this class last year. Okay, so and then bit 0 in the first exchange is designates whether this is a streaming or a single transaction, meaning that if it's a single transaction, you would have the master would have a 0 in this bit position, and that would mean that it wants to read or write, or it intends to read or write 1 byte. And if the bit 0 in the first exchange is set to 1, then that would indicate this is a streaming transaction. Now, I haven't really used that term much in the class, streaming, but all that means is that instead of just reading or writing 1 byte, you're reading or writing multiple bytes, more than 1. And you might say, wait a second, I mean, if there's multiple bytes, I mean, there's only one address. How can you have multiple bytes if there's just one address? And that's why we use the term stream, because if you do a multi-byte read or write, it is assumed that each of the bytes that are read or written correspond to consecutive addresses starting at the address that was in the first exchange, right? So what this means is that so this address is a 6-bit address. In hex, it would be 1 1 in hex, right? Because there's a 1 in the first 2 bits and a 1 in the last 4 bits. So you group these bits you group the address bits in groups of 4 starting from the right. So 1 1 is the address, and if this were a streaming access, then the first read or write would be at that address, and the next one would be at 1 2, and then 1 3, and then 1 4, right? So that's the idea with streaming. And then if it's a read, then the MISO would have the read data in exchanges 2 in exchange 2 and any exchanges that happen after that. And if it's a write, then it would be the MOSI, so the master would be sending the data. Okay, so that's yeah, so that's my trying to annotate this out. Okay, so the expectation for your code is to read this from the trace file and print a very concise output that literally just says RD 111A. So the RD means read, and then the 11 is the address, and the 1A is the data that was read. So this is all your program should print after having read this. So here's an example of a write. In this case, the read-write bit, which is bit 1 in the first exchange, is now set to 1, meaning this is a write. Also, the address changed too. And then, of course, now that there's data in the second exchange, we have data on MOSI instead of MISO. So this is a write. And so the address here is 3, and then 1011, which is B, so 3B. And then the data is 39, so 0011 is 3, and then 10019. So your program, if it sees this transaction, should just print WR for write, and then 3B39. Nice and concise. So it's basically, the idea is you're converting these waveforms, these traces, into these little messages that indicate the activity or what the transaction, what action the transaction has performed. Okay, so now let's look at a streaming example. So in this case, we have an address the address is always in bit 7 down to 2 in the first exchange. The bit 1 is 0, which means we're doing a read, but then bit 0 is a 1, which means we're doing a stream. Forgot the N where, Charles, I'm sorry. Where?
Unless I made an error and somewhere, the intention was that the first byte would be the sent from the master to the slave would be as it's shown, and the second byte would be sent from the master to the slave and would have the number of bytes that were to be streamed.
Oh, okay. Sorry, I might have missed that. Okay.
Yeah, that's how the I think that's how the test case generator and stuff worked. Otherwise, I really screwed up there, but I thought that's how I'd written it.
Yeah, that might be the case. If that's the case, that's no problem. We can change that. So so in this case, the second byte from the master to the slave. Sorry, I think I just didn't read I didn't read your lab sheet closely enough. Yeah. So the second byte is actually going to be. Let me just update this. Yeah, sorry. No, it was my fault, Charles. I didn't read it closely enough. So, but I'm glad you're here to correct me. Okay, so this is the number of bytes. Okay, so this would just be in the second exchange. Okay, the second exchange, and this would be from MOSI to MISO. So in this case, you know, obviously 0 wouldn't be a valid value. It would be I would assume greater than 1, right? So that would be 2 or more here in the number of bytes. And then from that point, you would have the data coming back on MISO. And so in this case, and then, you know, the output or the program would be read and then stream and then the address followed by the bytes. So in this case, let's update this a bit. Yeah, so let's update this a bit. Let's just pretend for now that we just did 1. So we'll just update this so it makes sense. We'll assume that's 1, and then the value is, instead of 39, it's actually made A7. Okay, so hopefully that didn't confuse you guys too much. So the protocol is now the reason I was confused by that was because in the past when we've used these streaming interfaces, I thought the number of bytes was just determined by how many exchanges we held the slave select down. But as I mentioned, you know, you can do this however you want as a vendor who's developing a a peripheral that speaks SPI. You can build whatever protocol you want. So in this case, you know, you want to interpret the second exchange as being the master telling the slave how many bytes. All right. Okay. And then and once again, when you write, it would be the same thing. So let me just update my picture here to show that. Move this over here. There we go. Okay. And then in this case, we're just going to write A7. And this would be, I'll update these slides and post them online. I haven't. And then so we've got, in this case, we're going to write 1 byte. So we indicate that by setting bit 1 is 1 indicating a write, bit 0 is 1 indicating a stream. So in the second byte that we send over to the slave would be, in this case, 1. Because we're only sending 1 byte, although typically this is going to be more than 1 because we're streaming. And then the following byte would be the first of the bytes that we're streaming or sending out to the slave. And then you would print write stream 3B A7. 3B is the address, A7 is the first byte that we're streaming, and then if there was more than 1 byte, then they would be listed there right after A7, separated by spaces. So that's it. Okay, so that's parts 1 and 2, and then in part 3, as I mentioned, the CPOL and CFA are not necessarily going to be 0, 0. They can be any of the other 3 combinations. So Charles had to decide how he would communicate that information to the program, and the easiest way to do that is to just add CPOL and CFA as signals in the trace file, but these signals will be constants. They won't change. They'll be, basically flat lines, if you were to view these like on a waveform. But it's convenient because, as Philip mentioned earlier, you can read the CPOL and CFA at time 0, and that will tell you what to expect in terms of what the CPOL and CFA were set to when the signals were generated, and then you would just interpret the data based on those CPOL and CFAs. So that would imply that you have to change the timing, the time at which you read the bits has to be updated. So that is all. And just to refresh everyone's memory, CPOL is the default value of the clock, and CFA is when the data changes relative to the clock. So if CFA is 1, you want to read the data on the second edge of the clock, starting with the second edge of the clock, whereas if CFA is 0, you want to read the data starting on the first edge of the clock, because the data would have already been established by the first edge of the clock. So you might say, well, that makes sense, but why do we care about CPOL? Well, you care because the first and second edge of the clock, whether they're rising or falling, will depend on CPOL. So you have to be careful when the CPOL will determine whether the first and second are rising or falling, right? So that's important. And yes, Charles mentions the bit order is fixed in the lab. So Charles says that he believes it's most significant to least significant. That is technically not fixed in SPI in general, but in this lab we're not worried about. We're not going to make you have to be able to deal with the different bit orderings. So that's it. Sorry for the confusion. I'll update this slide though, and I'll post it online. The only problem is that it's going to require me to squeeze this in a little bit, because we're going to need at least 4 transactions to show a stream with 2 bytes. Yeah, Charles's opinion is it doesn't matter. It's not interesting to do bit ordering. Okay, that's fair. Okay, any questions? Okay, all right, so let's now jump into the next lecture. Real-time scheduling. So we started talking about this, but it's been a little while, so I'm going to kind of just start from the beginning here and introduce this, and then hopefully we might be able to finish this lecture after Wednesday. Okay, so what is real-time scheduling, or what is a real-time operating system? What is that all about? It's basically, recall that operating system has to schedule the CPU. So it has various tasks, various processes, and it has to decide which one is getting to use the CPU at any point in time. So basically, the operating system is assigning each executing task to a specific time interval on the CPU. Now, the problem is that depending on how it decides to schedule the tasks will finish at different times. Now, in a normal operating system, you don't really care when tasks finish necessarily. At least there's no constraints. We're not forcing the operating system to ensure that each task finishes by a certain time. However, if you have a cyber-physical system, you most certainly will care when the task finishes, because you're interacting with the physical world. You're implementing a controller. You're trying to control the world. You're trying to control something physical. And if the thing you're trying to control has dynamics, as we modeled with the time invariant linear LTI, the linear time invariant system, then you have to make sure that you maintain a certain sample rate or update for the controller, or else the controller may not be stable. So that's what real-time scheduling is all about. This is very common in any computer system that is controlling something in the real world. The problem is that real-time scheduling is really hard, and one way the one way you know that is that there's essentially no real-time operating systems available sort of that are free or open source. It's kind of a specialized area. And part of the reason why that's the case is that it's difficult to do real-time scheduling. It's a very hard problem, and it's still sort of an open problem. One of the issues with it is the measuring worst-case execution time of a task. In order to do real-time scheduling, you have to know how long it takes to run, and there's a lot of uncertainties in a computer system. There's a lot of aspects of a computer that's non-deterministic. You've got cache misses and interrupts that may happen unexpectedly. It's difficult to necessarily tell how long it takes to run a program. So one way to do it is to kind of handle it statistically using empirical measurements. Now another, you can measure a task running on a CPU and measure how long it takes, or you can also model it like in a simulator. But the problem is doing that, you end up with this statistical distribution. And so in this case, we can assume that, it's common to get sort of a Gaussian distribution. And so as you know from statistics, you're not going to have a sort of upper limit to the value you might get from a Gaussian random variable. So you can use confidence intervals to estimate that. And so, for example, I added this slide. Let's say you have a task and you measure 10 runs, and it takes 12 milliseconds, 13, 10, 14, 11, 30, 27, 25, 31, and 32 milliseconds. And you want to know what the worst case execution time is with a 99.9% confidence, assuming that all of these come from a normal distribution. So you're assuming that the application doesn't really have any kind of data-dependent behavior, and so its control flow is always the same. So to figure this out, you can take the mean, which in this case is 20.5 milliseconds, and the standard deviation, which is 9.2 milliseconds. And you can calculate the worst case execution time by taking the mean and adding that to 3.09 times the standard deviation, which gives you 48.9 milliseconds. And so you look at that and you're like, wow, that's a really high number compared to all the ones I saw. The highest one I saw was 32 milliseconds. But it could also be that the first 5 runs were resulting from a one control flow through the program. So the task may have data-dependent behavior. In other words, it may take a branch or a series of branches in basically 2 configurations depending on what it's doing. In which case, what you really have is 2 normal distributions. So if you assume that, like, let's say, for instance, that the first 5 and the second 5 measurements were generated by 2 separate control paths through the program, in which case you can calculate the mean and the standard deviation of both of those separately. So it's 12 milliseconds is the mean of the first 5 measurements, and 29 milliseconds is the mean of the second 5 measurements. And the standard deviations are only 1.6 and 2.9. So you might say, well, what is the advantage? Well, the advantage is that this gives you a much tighter measurement. The standard deviations are smaller. So the worst case execution time would simply be then the maximum of the worst case execution time of each of those 2 control paths, which would be 12 times 3.09 times 1.6 for the first control path, and 29 plus 3.09 times 2.9 for the second control path, which gives you 16.9 milliseconds and 38 milliseconds, which the maximum of those 2 is 38. So look at the huge difference. I mean, 38 versus 48, just having a little bit of knowledge about how the task works, how the program works, you can get a much tighter execution time bound, which it's nice. But you have to obviously understand. You have to know a little bit about how the task works. So, but that's how you that's an example of a way to estimate the worst case execution time. Okay, so what about scheduling? So tasks can be in a number of different states, but there's 3 main ones. There's ready, which means it's ready to be executed, but it's not being executed, so it's kind of waiting. Then there's a sleep, which means it's not ready. It might have completed execution time, or maybe it's waiting to be dispatched, or it's waiting for an interrupt, or it's waiting for something, but basically it doesn't want to run. It exists, but it doesn't want to run. Not at this time anyway. And then executing is when you actually have the task assigned to the CPU and the CPU is executing that task. So those are 3 main. There's in reality, if you look at an OS, there's more states than processes can be in a lot more states than just those 3, but those are the main ones, the primary ones. Okay, so in a real-time operating system, each task will have a deadline. And so let's just imagine that we have 4 tasks, and each of them have a worst case execution time, and each has a deadline. And so we have 24 possible ways that we can schedule those tasks, assuming that whenever we schedule them to run on the CPU, we run them to completion, meaning that there's no preemption. We don't preempt. We don't stop a task that's already running. So there's 24 possible ways to do that, just 4 factorial, and I generate these, and this is a little bit confusing, but I generate these as a waveform where the tasks are marked on the waveform as 0 or 1. 1 means they're running, 1 means it's running, and 0 means it's not. And you can only have 1 task running at a time, because in this case we're assuming that we only have 1 CPU. We'll look at multi-core CPUs a little later. But if you only have 1 CPU, you can only run 1 task at a time. And so depending on what order you run these tasks, you may or may not meet all the deadlines. Well, it turns out that out of 24 possibilities, and by the way, I kind of just randomly chose these numbers, and I didn't sit there and like even try to massage them. These are sort of just ad hoc numbers I put in, and it turned out that out of 24 possible schedules, there's only 2. I think, was it 2? There was only 2 that actually satisfied the deadlines. It just coincidentally happened that the second of the 24 that I generated when I was enumerating these things met the deadline. So let's look at an example of where we meet the deadline. So if you look at task 1, I have these little red lines indicating where the deadline is. So task 1 was run, task 4 was run first. And then task 3 was run second. And task 3 just barely made its deadline. You can see that it went from running to asleep right before its deadline, shown by the red line there. And then task 1 was run third, and it met its deadline, and then task 2 was run fourth, and it met its deadline. But if you look at the first schedule, we ran task 4 first, task 3 second, which was so far is the same as the last one we looked at. But the difference is that we ran task 2 third, and then task 1 fourth, and that caused task 1 to miss its deadline. And so out of all 24 of these, almost all of them missed their deadline. We have one here, task schedule 8, I think was the only other one that met the deadline, where we had task 3 was run first, task 4 second, task 1 third, and task 2 fourth. Yeah, so you look at these, they have every possible one plotted there. They all miss. So there's different strategies for doing the scheduling, as opposed to having to, obviously fully enumerating them is not a good solution, especially if you have a lot of tasks. So there's these scheduling policies. For example, you might hear like shortest task first, earliest deadline first, or least slack first. So for example, one way to do it is to schedule the shortest task first. Well, in this case, task 2 is the shortest one in terms of execution time. It's only 6 milliseconds. So if we schedule that one first, then task 3, which is the next shortest, at 14 milliseconds, then task 4 at 20 milliseconds, and then task 1 at 40 milliseconds, you can see that actually didn't work because task 1 missed its deadline. Actually, task 4 missed its deadline too. So we have 2 tasks that miss its deadline. Earliest deadline first is when you schedule the task with the earliest deadline first, which in this case gives us task 4 first with a deadline, task 3 first with a deadline of 35, then task 4 with a deadline of 37, then task 1, and then task 2. And you can see that was actually one of the 2 schedules that worked. And then another option would be to schedule the one with the least slack first. The slack is just the difference between the deadline and the execution time. So I added a table here that shows the slack, and you can see that task 4 has the least amount of slack. So we schedule that one first, then task 3, then task 1, then task 2, and that one actually met its deadline, met its deadlines too. So those two seem to work out, those 2 strategies. Now the question is though, how do we know if they're going to work though? Is there some criteria that we can apply to the list of tasks, their computation time, and their deadlines to determine whether they'll meet their deadlines under these policies? And that's what I'll talk about on Wednesday, because we're about out of time for today. Does anyone have any last minute lingering questions about the exam or the lab? Okay. Okay, good. As Charles mentioned, the lab sheet is up. It's very detailed. Has all the hopefully if you look through it, it'll it'll clarify things. Hopefully I didn't confuse you with my introduction, but I'll update my slides and post those online in case you want to see some waveforms that show what's going on conceptually for the lab. And like I said, you have 3 weeks. Submission link is posted. So let us know if you need. By the way, if you need one-to-one help with the lab, like office hours, send us an email, and one of the 3 of us will be happy to help you out one-on-one. Okay. Well, thank you, and I'll see you all on Wednesday.